Let's now talk about the final fourth case for deleting a node from a binary search tree. So far we talked about three cases. Let's do a very quick recap. What are the conditions for the three cases that wouldn't satisfy? That's why we have to go for the fourth case. The node P that we want to remove is not external, meaning that it's internal. You might have a left child or right child. And we are not satisfying this case over here where the child nodes are actually external. And also we are not satisfying the condition where the child nodes, one of its child nodes is internal. So what does that mean? That means both child nodes are internal. That's the case that's missing. Okay, so that's the fourth case over here. So we are talking about an internal node to be removed, and both of P's child nodes are internal. So that's going to be the tricky case that we got to handle. But let's see how we can do it. And before I actually go over about the general principle, I think this case is actually trickier than other three cases. So I better visualize a bit first before we go back, before we come back to the general principle. Let's do that. Right. So we have to subdivide the case number 4 into two different cases. One will be easier than the other, but let's now do both at the same time. The case number 4.1 is going to be removing the node with the key 17. Let's try. So 44 start with the root, 17 less than that, and we're lucky we have found it. Of course, in general, you may have to go down level by level down to the node that actually has the hits, or maybe you wouldn't be a successful search. And in this case, this 17 over here will be the P that's returned from the search routine. Right, this will be P. And just don't forget, we actually talk about the P that's to be removed, right? That's the variable name we are using as before. Okay, so that's a P. What about case 4.2? For case 4.2, we want to remove the node with the key 88. So start with 44 over here, and it should go to the right. So 88. And we're lucky, that's the node we want to remove. Let's now try to circle that to identify that's the node to be removed. And this node is actually P. And let's now double check, like both cases are satisfying case number 4. In which case, the P's both child nodes should be internal. You can see left child over here is internal. Right child over here is also internal. Similarly, for 88, left child is internal, right child is internal. And let's see how we can deal with them. The principle will be after you have removed either this node over here or this node over here, you have to do some compensation in such a way that the in-order traversal of the resulting tree will still be a sorted sequence. And you shouldn't really miss any other node. You should only remove this node that's to be removed. Let's try to take a look. Before that, let me try to give you some very general guidance over here. And let's review what we did earlier about in-order traversal. Let's just review that quickly. So when we talk about in-order traversal, and not to really focus on any specific example, I want to talk about the general recursive pattern. Let's say this is the root node that we start with over here. And let's say the root may have a left subtree, and also you might have a right subtree, right? And we know that they can be arbitrarily complicated. And in this case, let's assume at least there's one node in the subtree, right? This is 1, and this is 1. Right? You can think about this is left subtree, and this is right subtree over here. Okay. If I want to do some in-order traversal, right? Now here's my question I want to pose to you. You can pause the video after I pose the question. Let's say this is the root over here. Okay. Let's say this is the root over here. If I want to do some in-order traversal on this particular tree, right, it's going to be something, 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 and then there will be one node I need to visit before R, and then there'll be one node I need to visit after R, and after that it should be ... again. So my question is as follows. If I want to do an in-order traversal on this particular tree, starting from the root R, what will be the node that will come before R? And what will be the node that will come after R when I do the in-order traversal? Can you identify exactly where this node is and this node is in the diagram over here? Alright, you can now pause the video and think about it. Alrighty, assuming that you thought about it, in general, if you want to do in-order traversal, the node that comes before this, let me use green, should be over here. To be more precise, it should be the rightmost node on the left subtree. The rightmost node in the left subtree. Of course, in the extreme case, it could be that this is already the rightmost node. We don't have any further children. In that case, of course, it will be something like this. This is the left child of it. We can think about this is the left subtree over here, right? There's only one node over here. So the node that we're talking about over here is really this node over here, which is 8. 8 will come before 17. It's like this node will come before R. In the more sophisticated cases, let's say this. This is 88, right? Over here, you can see this is the left subtree over here. And the rightmost node will be not this one here, but this one over here instead. The rightmost node in LST, this will be 82. To be more precise, it should be the rightmost internal node. But since we don't really count the value for external node, so that should be clear in the context. So in this case, it would be 82. That'll be the rightmost node. That should really come before the 88, right? If you do the in-order traversal, it's a very important insight for you to see, right? That's the one case. That's one side of the story. The other side of the story would be what would be the node that comes after the R. That should be kind of symmetric, right? What should that be? Well, that should be as follows. That should be, let me use the red. It should be the leftmost node on the right subtree over here, right? Let me just write it down over here. So this should be the leftmost node in the right subtree. Notice the symmetry over here. One is about the rightmost, the other one is about the leftmost, and one is about the right subtree, and the other one is about the left subtree. Right? Just be careful about what we're talking about. For example, over here, let's say this. If I got this root over here, what will be the next one that's going to be in the in-order traversal after 88? It should be the leftmost node over here, 93, that's actually on the right subtree. Right? What about in this case? What will be the in-order traversal node after 17? The right subtree over here go to the leftmost internal node, which will be 21. 21 occur exactly after 17. So this is a very important insight for you to understand first. If you got any doubts, that might mean there's a gap in your understanding for the in-order traversal. You may want to revisit the lecture video from earlier. All right. Understanding this, we're going to now talk about the general principle about removing the nodes in this case, where the node to remove will actually generates two orphan subtrees over here, left and right, and also left and right over here. And let's talk about how we can fix the binary search tree after the removal, the compensation. Let's now go over the principle. Okay. So let R be the rightmost internal node in piece LST. That's exactly the kind of the node I was talking about. And in the slides, I'm basically talking about, let's say if you want to remove this node specifically, you want to find out what is the largest value, what is the node storing the largest key value that's strictly smaller than this node value over here. Apparently, it would be the rightmost node in the left subtree, which we just spoke about. That's why I want to talk about this general guidance before I go over the principle with you, right? So that's exactly what you will see over here. And you want to make sure you really understand exactly what these two lines are really saying, right? If you choose the rightmost internal nodes from the left subtree, it's guaranteed it will be the largest key value that's actually smaller than the node that we're looking for, right? And I believe there's a little typo over here. I'm going to fix it on the slides, right? So this one here should be P rather than N, right? So it should be the node that we want to remove. Okay, I'll fix it. Okay. And the exercise will be, is it possible that you can find alternatively, rather than the rightmost internal nodes from the left subtree, can we find the leftmost internal node from the right subtree? Basically, rather than finding this particular node, which is over here, if I want to remove this node, let's say, if I want to remove this particular node, rather than finding this node over here, which is corresponding to its predecessor in the in-order traversal, can I find instead this node in the in-order traversal, its successor, which corresponds to the leftmost node in the right subtree? Can I do that instead? That will be some mental exercise for you. You can think about it and maybe write down your argument on the paper. You can definitely check it with me if you want to. Okay. And of course, this part over here should also be P. I'll fix it. Don't worry. Alrighty, so now what should we do? the step would be, we want to, first of all, overwrite the node P's entry by node R's entry. What does that mean? Let's take a look. Okay, let's say in this case over here, we know that the left subtree is over here, right? Let's now highlight it. This will be the left subtree. First of all, this will be the left subtree. And how do we find the rightmost node in the right subtree? Well, in this case, this will be that one. In this is like a special case. This will be the rightmost internal node in the left subtree. That's what we have, right? And the principle will be, we want to not to remove it just yet, but we want to replace its key value over here to be here. So we just replace it by, let me just do in different step. Step number one, you want to remove, replace. Replace the key value over here rather than 17, you're going to replace it by 8. And also whatever element value that's associated with this node over here, you should set it as well, right? That's something you want to remember. So far, no detachment or attachment has been done. That's number one. Okay, step number one is about replacing. And I'll talk about step number two in just a moment, but let's talk about step number one. If I do this, am I still maintaining the search property? Indeed, because now if you got 8 over here, 8 is guaranteed to be still less than 21. So if you do the in order traversal, let me just do it over here. Used to be 8, let me just use, 8 is fine. Used to be 8 followed by 17 followed by 21 and etc. And we are trying to remove the node 17, right? That's what we're trying to remove. And the way we did it is by replacing the 8 over here for the 17 over here. So we still got 8 followed by 21, 8 followed by 21. So it's still maintaining the binary search tree property. So the resulting tree with one less node ultimately will still be a binary search tree. And how do we remove this node? That's kind of interesting, because in this subcase 4.1 over here, because this particular node is actually a node with 2 external childs, and this really satisfying case number 2 as we said before over here. So that's why we can apply case number 2 just as before. Okay, and for this one over here, that will be step number 2. To really remove this node over here, this will be step number 2. You can see case number 2 as we did earlier. So there are 2 steps over here. Number 1, to replace it. Number 2, to remove it according to case number 2. And you should really think about how to implement this in Java. Okay. Let's now talk about case 4.2 in a very similar way. If I want to remove this node over here, I should really find out what's the rightmost node in the left subtree, right? Let's now highlight it. So this will be the left subtree over here. Okay, that's the left subtree. And the rightmost node in the right subtree is actually over here, right? This one over here is the node, right? I believe we called it R over here. Right, so just by the way, so let me just make some quick annotation from before. So this rightmost node is actually what we call R in the slides, just in case you're wondering about it. It will be very important for you to identify it, otherwise you will have trouble with the implementation. That's R. And what about the R in this case? It will be the rightmost node in the left subtree, which is R over here. That's R. How do we remove it? Well, 2 steps, the same as before. What we're going to do is, step number 1, we're going to replace the node to be removed over here. Not to remove it just yet, but we're going to replace it by 82. That will be step number 1. And step number 2, we actually want to remove this particular internal nodes. That's what we want to remove, right? And you can see this is just another case. When we wanted to remove this rightmost internal nodes, that one there has 2 external childs. That's why we can apply case number 2. And for this one over here, that one there is not exactly case number 2 because it has 1 external and 1 internal. In that case, which case are we talking about? Well, if you go back there, it's exactly Case number 3, when one of the children is actually internal. Think very carefully about it, right? That's something we try to be very carefully trying to lay out the cases for you. And to remove this, let me just try to see that. So to really remove this over here, we need to apply case number 3. Case number 3 over here. So you can see, one is to remove the rightmost node in the left subtree using case number 2. The other one is using case number 3. Right? So you got two phases over here. And would this preserve the binary search tree property? Let's take a look quickly. Used to be, let's see over here. Let me see, where should I start? This is the node we want to remove over here. And the in order traversal, why don't we start with this one over here? Okay, used to be 65 followed by 76 followed by 80 followed by 82 and followed by 88 and then etc. That used to be the case, right? The node we want to remove is 88. And the way we did it is by replacing it by the 82 over here. That's the rightmost, right? Well, it's actually go right before that. So it would be as if we're just removing this. So its predecessor will just take the place over here. And then you can see if you look at the linear ordering over here, it's not going to compromise the order because 82 is still there. And then whatever element that goes after 88, what was that? After 88 would be 93 over here, right? Let me just put 93 over here. Just one more. Okay, and dot, dot, dot. So we still got 82 over here, 82, and followed by 93. It is indeed preserving the order, right? And one more thing to say. You can think about the 82 over here is really the largest key that is smaller than 88 that we wanted to remove. The largest is really the insight about manipulating the in-order traversal. Alrighty. Right, so these are the two sub-cases for case number 4. I think case number 4 is the most complicated one to really understand, so that's why I want to record that in a separate part. You really want to study carefully about this insight over here and see how we can apply the two different sub-cases, but they follow the same principle. You definitely have to do the replacement first by finding the rightmost node in the left subtree in both cases, and then do the replacement, and then to see how to remove that particular rightmost node, either by using case number 2 or by using case number 3. That'll be a very quick recap. Right, let's see anything else. And so these are exactly what I just spoke about. You can, one mental exercise for you. Think about why. Given that R is the rightmost internal node, given that, right? Why would it be only two sub-cases to consider? In this, for example, we're talking about either the rightmost internal node is called R, right? Either R has two external childs, or R has one external right child and one internal left child. Why can it not be the R over here actually has one internal right child and also one external left child? Why would that be? Why would it not be a valid case to consider? You can think about it, and that's the question for you, right? If you got any doubts about what I just asked, rewind it. It's a very important concept to check by yourself. Okay. Right, runtime is going to be dominated by the initial search over here. So that's why it's going to be same as before. It's going to be big O of H, the height of the tree. And as I said, I'm going to talk about the balance property about the binary search tree next week. All right, so that's about the several cases I just spoke about on the iPad, and you can just go over them on the slide as well. Final exercise for you, and you want to go to the BST utilities class over here in the source code and try to implement the delete. Right? There might be some implementation detail which you have to figure out, which I couldn't really cover in the slides. But I think for the general principle and visual illustration, it should be rather clear to you to continue with the developments. All right, so that's about the end of this lecture here about binary search tree, and we have covered quite many important and interesting details over here. Study them carefully, and next week we'll move on to balanced binary search tree.